Network Plus Series, TCP IP Addressing, Part 3. Well, I know what you're saying. You're probably thinking, wow, really, 3 nuggets just for this topic of TCP IP addressing. And the truth is, this is really an important aspect of networking. It's one of your key areas of design and troubleshooting. And in this third nugget, we have to cover several things. Now, I'm going to take an approach, first of all, right off the bat, probably the most real-world approach, well, for sure the most real-world approach you've seen so far in this nugget series. I'm going to start out kind of from scratch, looking at an organization, building our IP addressing and subnetting using CIDR or CEDR representation, the /24, /18, and so on. And then we're going to look at how we're going to implement network address translation and or port address translation into our solution. And then, based on that subnetting, we'll go and we'll configure DHCP. We'll show how to do it statically, and I'll show you again where to do a PIPA or a PIPA. And then we're going to finish up going through that OSI model, which I've alluded to so many times now, but we need to memorize all 7 layers. Okay, let's just literally start from scratch. Let's say I work for a company in the Dallas-Fort Worth area, and it's called Kiro Consulting. And by the way, this is a fictional company, and it's a name I used to use and still use. Kiro Consulting. We're in the Dallas-Fort Worth area. It's a pretty large consulting company. We work throughout all of North America and some in South America. So we have over 15,000 employees. So we're sitting down with our steering committee and we're going, okay, we need to figure out what type of IP addressing scheme we're going to function with. And let's say we're going to go ahead and we're going to choose the 172.16.0.0 address space. Now we know from earlier this is a class B address space, but we're not going to use any classful system. Okay, none of the routing protocols that we're going to be using are going to be old school, and we'll talk about routing protocols later. But we can say, look, we've got this particular 172.16.0.0, which would normally be the prefix of 16, which means the first 16 bits are for the network and the second 16 bits are for the host. But if you look at these 16 bits here we have for the host, on this network of 172.16.0, that gives us 2 to the 16th power minus 2. Remember, 16 bits here for host. And that is just absolutely way too much. It's like 65,534. And we can't do what we've done before, which was say 172.16.0.0/24, which was the old class C, which said the first 24 bits are the network and the final 8 bits are the host, because that just gives us 2 to the 8th power minus 2 bits for our host, and that's 254 total addresses. Well, obviously, neither one of those is workable. So we want to find something that's somewhere in between. And since our company has about 15,000 nodes in it, we'd like to find something that provides for these 15,000, but also has a little bit of growth in it. So if we look at this, and I'm going to draw out a chart right now that's going to help us come up with this decision. This is probably something you're going to want to go ahead and write out when you take your exam. This is the number of bits. So again, we have 8 bits from the high order 8-bit to the low order 1-bit. This is the power, 2 to the 0 power, 2 to the 1 power, 2 to the 2. This should be 3, sorry about this, 4, 5, 6, 7. 2 to the 7th power. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16. Okay, good. Then these are our subnet masks, and these are our prefixes. Now what we're concerned with here for this organization is this third octet right here. And we know that we've already determined that 172.16 255.0.0 with a mask of 255.255.255.0 is not going to cut it for us because it only gives us 254 hosts, right? So what we want to do is we're going to borrow some bits, because these 8 bits, these are network bits, these are network bits, and these are network bits, and these are host bits. What we want to do is we want to take some of the network bits in this third octet, and we want to turn those into subnetwork bits. In other words, we're going to break down this one, what appears to be a single Class B network, into multiple subnetworks or business units, we'll call it that way, business units based on what Kiro Consulting needs. But we're going to start out, first of all, by looking at what is the address space that we want to work with based on the total number of hosts. Now, we know that if we go with this mask, 255.255.255, we're using 24 bits. So this is /24. We're using 24 bits for the network. Well, if we went ahead and said, look, let's take one of the bits from this third octet and make it for subnetworks, we would now have a prefix of 23, right? 23 network bits, and now instead of 8, we'd have 9 host bits. Well, 2 to the 9th power, okay, we know that 2 to the 8th power is 256. 2 to the 9th power gives us, let's just get the calculator. 2 to the 9th power, but minus 2, by the way, that's 510. So if we change the prefix to 23, that gives us now networks of 510 hosts. That's not enough. We got 15,000. Well, let's clear that out. What if we change this and say, well, let's make it /22, where we've got 22 bits for the networks, which gives us now 10 bits for the host. So 2 of the bits here are going to be subnet bits. Well, let's see what 2 to the 10th power is. Obviously, if we just double 2 to the 9th, we'll get our answer. But 2 to the 10th minus 2 equals 1,022. That's getting better, but that's not going to do it. 2 to the 11th power minus 2. Remember, we're subtracting 2 because obviously we can't use the network portion. We can't use the broadcast. Is 2,046. All right, well, we're getting there, okay? Let's just jump up to, I don't know, how about, let's just say let's go ahead and do 18 network bits, and 32 minus 18, if we do the math, leaves us, I think it's 14, okay? So if we go with the /18, we've got 18 bits for the network and 14 bits for our host. So 2 to the 14th power minus 2 equals 16,384. That is more like it, because it accommodates for our 15,000, and it gives us 1,382 extras. So we got room for growth. That's perfect. So instead of going with 172.16.0.0/16, let's go /18. Well, that's going to change our subnet mask, because before it was 255.255.255. Well, now, if we use these first 2 bits, if these are now our subnetwork bits, this is the third octet we're looking at right here. Okay? If we take these first 2 bits that used to be host bits, and now we make them or bar them and make them subnetwork bits, we now have a mask in the third octet of .192. How do we get that? Well, we add the value of the high order bit, 128, plus the value of the second bit, which is 64. We're turning these on, and that's a mask of 192. So now our overall network is going to have a network of 172.16.0.0 with a mask of 255.255.192 0.0 or /18, which means the first 18 bits are being used for the network, and the remaining 1, 2, 3, 4, 5, 6 bits of the third octet and the remaining 8 bits of the fourth octet, 14, 2 to the 14th power minus 2, host bits. Now, we've got a different scenario here. Instead of having 65,534 hosts, we've now got 16,382. But what we've also done is this. Since we're using 2 bits for the subnets, we've actually also created for ourselves additional networks or subnetworks. As a matter of fact, since our subnetwork boundary is right here where it's 64, our subnetworks, we're going to have 4 of them. We're going to have, and let me clean this off a little bit. So our networks are now going to be 172.16.0.0, 172.16.64.0, 172.16.128.0, and 172.16.192.0. Now we can't go up. If we add 64 to 192, that gives us 256, and that puts us up in the next network, 172.17, so we can't go there. We've now got 4 big networks. Each of these networks has 16,382 hosts on them. Now, how do we know we have 4? Well, how many bits are we borrowing to create subnetworks? 2. So 2 to the second power is 4, right? Because we can use the 0 network and we can use this top network. So we get 4 networks. 2 bits, 4 networks. If we borrowed 3 bits, we'd have 2 to the third power or 8 networks, but if we'd have fewer hosts. As a matter of fact, we'd have half as many hosts per network. Makes sense, doesn't it? And then our mask would be .224, and the prefix would be /19 instead of /18. And so what you're going to do is you're going to use this CIDR prefix to vary the length of the subnet mask to get just the right network you need for the number of hosts you need. We're going to take this even further. In this particular first block here of addresses, we'll even vary the length of these and break it down in even more. This could be a business unit, and then we could vary the length of the subnet mask and use CIDR prefixes. Let's say we could have a bunch of networks with a /21 prefix, and then within those networks we could have networks with a /24 prefix and just break it up into smaller units. Now the reason why we do this is because if we have a network down here with a /24 prefix and they've got a router servicing that network, if one of the hosts on a switch that connects to that router, or the switch ports going up and down and causing problems, it's not going to affect all these higher networks. Why? Because our routing table is going to do a process called summarization. We're going to aggregate all the routes into one entry on the routing table. Now we'll talk more about that in routing, and it's really beyond the scope of Network Plus. I'm getting way too advanced for you, but what I'm talking about here is the importance of IP addressing. Now that we've gone through all that rigmarole, what we have to decide next is this. We're using an internal IP addressing scheme. We're using one of these from the Request for Comment 1918, which means these cannot be routed on the internet. So we want to use a process called network address translation and port address translation so that we can use these private addresses internally, and then on the outside of our network, outside of our router that connects to the internet, we'll use one or a few public IP addresses that we purchased from our service provider. Let's talk about NAT and PAT next. Now the advantages of NAT, network address translation, is that on this side of our firewall or our NAT device, and the NAT device could be a wide variety of networking devices, but on the inside of our network, we can use any network addressing scheme we want to. For example, we can use 172.16.0.0/18, which means our address range is going to be 172.16.0.1 is the first available address through 172.16.63.254. Okay, this is our range, and this is actually 16,382 addresses. Now, we can't use 172.16.0.0 because that's our network. And we can't use 172.16.63.255 because that's the directed broadcast on this network. And by the way, if we go up one from 255, which is the broadcast, the next available address is 172.16.64.0. We can't use that one because we saw earlier this is actually the second network when we use this /18 prefix, or a mask of 255.255.192.0. So what we're going to do is we're going to use NAT to allow us to use any old addressing scheme we want to do, and then we'll translate that into a public address, or let's say a routable address, let's say like 157.54.10.1 out here on the internet. It accomplishes two things. We are able to get around the limitations of running out of IP version 4 addresses. And secondly, it's a security mechanism because it hides from the outside world and our malicious attackers, as little horns, our malicious users out there. We hide the internal IP addressing scheme from the malicious user so that they cannot use that information against us and attack our network. So it provides two things. Now, what network address translation can do is a wide variety of translations. You can translate your internal IP addresses, let's say .1, .2, .3, .4. We can translate these. We could have, for example, a DMZ right here that has public servers in it. Let's say web servers. Maybe it's got FTP servers. Maybe it's got mail servers, SMTP. Other content servers as well. We could also use private addressing for these servers, and we could translate these also into a public addressable scheme like 157.54.2.11.1.2.3 and so on. And again, we're hiding the actual IP address of these servers for a layer of protection and for IP address resource utilization, not wasting IP addresses. They're expensive and they're rare. Now, that's what network address translation does. We don't have to worry about configuring it. But what does PAT do? What does port address translation do? Let me clean this up and explain it to you. PAT says this: we're going to take one address on this interface, and this may be connected to your ISP. There may be a router here as well, but we're going to represent our entire network, our entire organization, as one address, 157.54.0, or how about .10.1. This is the IP address of our organization, Kiro Consulting. Everybody who wants to get access to our organization outside here on the internet is going to see us as this IP address. Now, remember what's happening is we've got users on the inside of our organization here, the inside, and we have a demilitarized zone over here, which is a special area for servers, okay? Web servers, e-commerce servers, the servers that the public access. So, these users are going to be the ones that are creating the connections and the sessions with the outside world. We're not going to let any of these users out here create connections with the outside world and just come through this firewall, willy-nilly. We've got email servers out here that are going to handle this and intercept this and then communicate with us inside. But we know that we're using 172.16.0. and whatever, .1, .2, .3, and so on inside of our network. What port address translation does is it also uses a port number and it combines a port number, let's say colon 2002, and it does a translation from the internal private IP addressing scheme to the public. So each one of these hosts, as they create connections to the outside world, as far as this outside world is concerned, they are 157.54.10.1.2002, 2003, 2004, and so on. And what happens on the firewall is the firewall translates from this one IP address and these port numbers to these inside private IP addresses and the actual port numbers that they choose to use in their communication. So we combine translating the addresses from the 172.16 space to this public addressable space, and we can overload this one single IP address and represent our entire organization as one IP address by combining a port translation. Now we know that the ports that we have, the TCP and UDP ports, this is a 16-bit number. So we have 65,536 ports. Now we can't use all of those, but you can see we have greater than 65,000 ports. So one IP address can be translated into over 65,000 internal addresses. And if we need more, we'll just go to the next available number here, and we'll have two IP addresses on the outside, .1 and .2. And that is how Nat and Pat helps our organization use private addressing, but also have the benefits of a public IP address. It also allows us to accommodate for different types of scenarios using IP addressing and get a level of security by hiding our internal IP addressing scheme from the outside world. So once we get our classless IP addressing scheme, we figure out what our subnet mask is going to be, and we know we've got network address translation and port address translation. We can now go to our client. I'll just use my wireless one here, and I'll just go to the properties and configure on my Vista machine this wireless client. Now notice my Vista machine by default, I have an IP version 6 device driver to support that. I can go, configure the properties, obtain it automatically, or use a static IP version 6 address. I can do that, or we can do IP version 4, and we can say obtain it automatically, which is using a DHCP server, or I could use the following address. Now if I'm going to do this, I'm going to stick to my addressing scheme, which is 172.16.0, and again, .1 is probably going to go to a departmental multi-layer switch or a router. Let's say I am .11. So that's my static address. The mask we're going to use, remember, it's not 255.255.0.0, and it's not 255.255.255.0. It's basically 255.255.192.0. And my default gateway, most likely, is going to be 172.16.0, probably the first available address. It may also be my DNS server as well. And so what this 192 says here, it says we're taking the first 2 bits of the third octet and we're using those for subnetworks, creating 4 subnetworks to be exact, which leaves us 14 bits, okay, 8 from the last octet and 6 from the third octet for our host. So we know in this situation our valid range of 16,382 addresses is 172.16.0.1, which is the router's address, through 172.16.63.254. 255 is the directed broadcast on this very large network of 16,382 hosts. You can always verify this by going up and downloading a free subnet calculator and checking it out on your own. Getting a subnet calculator off of the internet is one of the best ways to learn how to use this CIDR prefix and variable length subnet masking for classless IP addressing. I can always cancel out of here. If I go to Properties, notice the Alternate Configuration tab. I might want to say, you know what, we'll go ahead and use DHCP or put in a static IP address, and I can say, if for some reason my DHCP is not available, use a PIPA or a PIPA. And that'll give me something from the 169.254.0.0 range. Or I can say, here's some user-configured backup IP address, mask and gateway, backup DNS servers, and backup Win servers. So with your alternate configuration, you have a couple of options. You can say I can fall back on a PIPA, or I can fall back on my own user-configured IP address. So I could say, you know what? I could say let's use DHCP, but if it's not available, let's use our own user-configured address as a backup. Excellent. I used to spend a lot of time talking about the ISO OSI model, the 7-layer model. I would spend a whole nugget doing this with a great allegory called the Fellowship of the Token Ring, and it's in my previous or the original Network Plus series. But you know what? I'm not going to do that this time, because the OSI model is really not as important as it used to be, because we don't really design networking solutions with the OSI model that much anymore, the 7-layer model. But I'm going to give it to you because they may test you on it, all right? And we've already talked about several of these layers, okay? And it is important because in networking vernacular, we allude to different protocols and services and mechanisms as layer 2 or layer 3 or layer 4. So let's start at the top. The application layer is exactly that. It is the user interfaceable application layer, like things like DNS, the domain naming service, simple mail transfer protocol, okay, the POP3 protocol, the applications and services that are network enabled. Your web browser is an application. The presentation layer is where information is translated. Syntax is modified. For example, file transfer protocol can transfer in ASCII or in binary. Encryption of information can happen here at the presentation layer. It's the way that information is presented. And so there is a translation or a modification from the application layer to the presentation layer and then on down. The session layer is interesting. This is kind of the traffic cop, I'll call it that. The session layer allows you, for example, on your laptop, to open up an instance of a browser session that's, let's say you're playing online poker. Then you have another browser opened up and you're checking your webmail. Another browser is opened up and you're surfing the web somewhere else. So you have multiple sessions. It keeps track of applications and services, multiple channels, or multiple communication sessions. It allows your operating system to have, let's say, instant messaging and a web browser and an RDP remote desktop protocol session and a telnet session. All these things opened at one time and functioning through the same network interface card. Does that make sense? The transport layer is where the data becomes segments. And we use two types of protocols here, TCP and UDP. And we talked about TCP and UDP, the transport layer protocols, the connection-oriented and the connection-less, the reliable and the unreliable, early on in this Nugget series. I'm not going to revisit that one. But the transport layer is very important. Then we have the network layer, and this is where routing is done. We have routing as far as your routed protocols like TCP IP, IPX, SPX, AppleTalk, DECnet, other routed protocols. We also have the routing protocols that we're going to talk about in the upcoming nuggets here. RIP version 2 and Open Shortest Path First, OSPF, and border gateway protocols, the routing protocols. Then we have services. The most popular service, for example, we talked about earlier, ICMP. The ICMP and IGMP protocols operate at the network layer. The data link layer is the bridge, the software bridge to the physical media. And this basically has two layers to it. There's an upper layer that interfaces with the network, layer 3, and a bottom layer that interfaces with the physical media, Ethernet, token ring, FIDI, wireless, whatever physical implementation. The physical is literally the modulation types and the mathematical techniques to convert information into zeros and ones, either to go on the wire or to go through the airwaves wireless. It's the modulation schemes, okay? So you have to memorize these from the top down and from the bottom up. And so some folks will give you like these handy little mnemonic tools to do that, like all people seem to need data processing, okay? Forget that. I want you to know these and just memorize them, okay? Physical layer 1, data link layer 2, network layer 3, transport layer 4, session layer 5, presentation layer 6, application layer 7. Now the reason why this is not so important anymore is because nowadays we literally combine these top 3 layers into the application layer now. So application layer is basically OSI 5, 6, and 7. Then we have a transport layer. Then we have an internetwork layer. And then you have the physical layer, which is kind of the link and the physical media. So it's a 4-layer model now. 1 and 2 is the first layer, network layer is the next layer up, and then so on. Now, we still refer to networking as layer 3. If you say layer 3 protocols, we're talking about RIP version 2, ICMP, IGMP, Open Shortest Path First. You talk about layer 4 protocols, you're talking about TCP and UDP. A layer 2 protocol, that might be point-to-point protocol, PPP. It might be frame relay is a layer 2 protocol. So we still use these OSI model labels to label different types of protocols. So even though we're not using the OSI model really to develop networking systems anymore, it is important when you hear terms like layer 2, layer 3, and layer 4 that you know what we're talking about in the OSI model. So for example, if somebody says a layer 3 switch, that should tell you that it is a switch that typically works at data link layer 2. It has layer 3 functionality in it. For example, it's a switch that has a route processor or a routing capability built into it. So layer 3 switch should tell you it's a switch that operates at network layer 3. Those types of things. That's the OSI model. Application down to physical, layer 7 down to layer 1. Got to memorize it. All right. In TCP IP Addressing Part 3, we started out looking at kind of a blank slate of an IP addressing scheme. I introduced that CIDR prefix along with variable length subnet masking to show that we can use a classless system to get just that right size of network. I also talked about the importance of NAT and PAT. I forgot to talk about SNAT. Frankly, I'm very surprised that the CompTIA people even added this as one of the requirements because SNAT is extremely proprietary. Okay, all different vendors have their own proprietary versions of secure NAT or source NAT. Some people call SNAT source NAT. Microsoft uses it for their secure NAT, which is part of their ISA server extension. The IETF, which is the Internet Engineering Task Force, refers to SNAT as SoftWire's Network Address Translation. So it's based on the SoftWire's working group. So, you know, this is a very confusing acronym. Again, I'm surprised that they even put it on the exam, but just so you know, SNAT. For practical purposes, think of SNAT to be used in an IP version 4 to IP version 6 translation process. So think of it as NAT interoperating with IP version 4 and IP version 6 in a transitionary state. There you go. Then we also looked at DHCP and static and APIPA options again. And then finally, that lovable, huggable OSI 7-layer model from the application layer 7 all the way down to physical layer 1. Well, that's it for TCP IP addressing, parts 1, 2, and 3. I hope this CBT Nugget's been informative for you. I want to thank you for viewing. See you later.